So today we're going to look at a special potential divider where we swap one of the resistors for a light dependent resistor, or LDR for short. If you haven't seen my video on normal potential dividers, I recommend you stop watching and see that first, as this video builds on the understanding you gained previously. I have linked it below. I'll be using a sine wave input just because it's better to visualize than a DC flat line. As this is purely resistive circuit, then AC input will make no difference to our results. Before we look at the LDR in a circuit, let's first gauge its characteristics. Here I have an LDR between two probes of an ohm meter, and we can see in natural light we're getting a resistance of about 11.4K. If I hold my fingers over it, it increases to about 150K. This would actually be higher if I could remove all light. Some LDRs in the dark can read into the mega ohms. Now if I shine a torch on it, off camera so my exposure doesn't close down completely, we can just about see it measures about 70 ohms. These are the basic characteristics of an LDR. It is a light dependent resistor, so it changes its resistance with light. In low to no light, it will have a high resistance, and in bright light, it will have an incredibly small resistance. This property can be very useful in sensor circuits. Let's now go back to our circuit with the LDR taking the place of R1 in the potential divider network. Here is our scope with the input on the yellow trace and the output of the divider on the blue trace. As we increase the light level, we can see the output rises, and if the light source is bright enough, we can almost meet our positive voltage input. With intuitive analysis, we can create three equivalent circuits. When the LDR is in low light, it acts almost like an open circuit, leaving the output grounded through R2. When the light level increases, its resistance drops, and it becomes almost like a normal fixed resistor for a given degree of light. In extremely bright light, its resistance becomes so small, it practically becomes a short, tying the output to the input. If we now swap the LDR with R2, we get this circuit. Analysing this on our scope, we can already see that in the dark the output looks just like the input. So our first equivalent circuit is that the LDR's resistance is so small that it shows almost like an open circuit. As the light level increases, the LDR's resistance starts to drop, and again into a more manageable resistance range, we can call this a fixed resistor to a certain degree of light. Lastly, when the light source is very bright, the LDR's resistance drops to practically nothing, and we can see our output grounds out. Our LDR has effectively become a short. Let's recap. Here we have two circuits, and below I have drawn an intuitive response curve. These curves are by no means accurate, but gives a basic understanding of the response. In reality, the curves would respond differently to different light wavelengths and temperature, etc. The change is not instantaneous either, so as the light level changes, the resistor will actually lag behind it. However, that said, something the graph shows us, which is very useful, is that we can create a rising or falling edge circuit. In sensor circuits, we can use this response to trigger a circuit when the LDR potential divider rises over a certain voltage, for example, or maybe when it falls below a certain voltage. In a future video, I will look into interfacing LDRs into logic, and it will highlight the use of the rising and falling edge more. So what effect does the fixed resistor have, I hear you ask? Well, let's take a look. Here I have two potential divider circuits, one with a 1K on the blue trace and the other of 100K on the pink trace. As I start to increase the light, we can see the 100K circuit rapidly shoots up to the positive rail, even with a very little amount of light, whereas the 1K slowly increases until full light is directly above it, and even then, it's only just hitting the positive rail. In reality, the 100K circuit is of little use as it is far too sensitive for what we want. Often a smaller value, say between 1K to 10K, is used in the form of a trimmer resistor, so you can adjust the sensitivity when calibrating the circuit. It's important to remember that LDRs are not precision components, which makes it very difficult to place them in a circuit and get a known response without any sort of tuning. Even LDRs in the same batch can differ in value and response. This is why most LDR circuits will require calibrating. This is commonly done by replacing the fixed resistor with a trimmer resistor. Or, if the circuit is using an ADC port on a microcontroller, for example, then you could actually use a fixed resistor and calibrate it within the software. Let's see a real circuit. Here I have an LDR potential divider driving the gate of a MOSFET which turns the lamp on when it gets dark. For our above analysis, we know as the light level falls, the LDR becomes more resistive, causing a voltage rise at the gate of the MOSFET, which will still start to turn it on. This circuit is incredibly poor without a Schmitt trigger, as the MOSFET partially conducts at low light levels, causing excess heating due to it being driven in the triode region. It fully conducts when completely dark and enters the saturation region of its response. The Schmitt trigger would clean up our response to use the MOSFET in either off mode or saturated mode, depending on the LDR being strongly lit or not, removing the dusk light middle ground that causes partial conduction. I will do a separate video about Schmitt triggers very soon and MOSFETs. However, for a very rough and ready circuit, it shows you how the gate voltage rises as it gets dark and the drain voltage drops as the MOSFET switches on and the load increases. On the scope we can see the yellow waveform is the LDR potential divider junction, or gate voltage, and the blue waveform is the drain voltage. Please don't worry if you're not sure what I mean with the MOSFET terminology. This video is not about MOSFETs, but I don't want you to experiment with this circuit thinking the MOSFET is like a switch. It isn't. It is a voltage control switch, which means it doesn't just have on and off. It can also have partially on, which is called its triode or linear region. To confuse matters more, the MOSFET used in this circuit is just a completely wrong MOSFET to use, but it is the only one I had to hand, so my results are not at all optimal. If you want to try this at home with a 5V power supply, you want to add a Schmitt trigger and a low threshold MOSFET suitable for 5V logic work. I will cover this in a separate video. In hindsight, maybe I should have just used a transistor and an LED, but that circuit is so common it was boring. I wanted to do something different. Ignoring all the issues with this circuit, you can see what I mean about the lamp turning on when it gets dark due to the resistance changing the LDR. That's all that's important in this demo. I currently have a project in post-production based around an LDR and a 4026B chip, which will be a great application of what you've learnt in this video. Hopefully that'll be out within the week or so, and I'll link it below when it's out. I hope this video has been useful. If so, please give it a thumbs up, and until next time, keep experimenting.